Okay, second part of the lecture on least squares approximation. So let's start back where we had left off. So we had just plotted these 2 points. And now let me remind you how you would do to find the line that goes through these 2 points. And I'm going to do it from a linear algebraic point of view. You probably know how to do it. Not necessarily this way. You've learned techniques, but here I'm really going to emphasize the linear algebra aspect. So what I want is a line with an equation of the form y equals ax plus b. So that's an affine equation, and which gives us just a straight line into space. So I want such a line that goes through these 2 points. So here, my x and my y's are going to be my data points. Okay. What I want to find are the values a and b that make a line go through these 2 points. So what I do is that I say, well, this line equation, what does it have to do? It has to satisfy the affine equation y equals ax plus b for the both values of x and y that we know. So the 2 points x and y that we have. So xy equals 1, 3 and xy equals 2, 5. So when I replace x and y by 1 and 3 in this equation here, what I get is 3 is equal to 1 times a, because x is 1, plus b. And when I replace x and y by 2 and 5 in this equation y equals ax plus b, I get this equation. And so what do we have here? We have a linear non-homogeneous, because here on the left-hand side we don't have zeros. We have a linear non-homogeneous system of equations. So you know what to do. We have this, we want to solve for a and b. Therefore, we write this in matrix form, okay? So the matrix is the coefficients in front of a and b. The unknowns are a and b. And the right-hand side is 3 and 5. Okay, so we've transformed this problem into a problem of solving a linear system, and you know what happens. Our famous linear algebra in a nutshell theorem that we saw during the review session states that this system, which is a system with a square matrix, so everything is nice, this system has a unique solution if that matrix is invertible. We compute this determinant, we find -1, so we can solve. Okay, I'm not going to do it explicitly here. I'll actually let the computer do it. But I'll show you later, okay? So now let's add a third point. So I edit my list of points by adding a third point here, 3 and 4. So this means that additionally to the 2 I had before, I'm adding the point 3, 4. When I plot this, you can see that these points that I have on the figure, they're not on a straight line, obviously. So it is clear that I am not going to be able to find a line that goes through these 3 points. We say they're not collinear, okay? They're not on the same line. Now, there's still a linear algebraic aspect to this. So we do as we did before, we write the system of equations, but now it's what we call an overdetermined system, because there is one more equation than there are variables. Okay, the unknowns are a and b, and there's 3 equations. We've checked that there is the points are not on a straight line, so we know right away that this system is not going to have a solution. If the 3 points were on the same line, we would find a solution. One of the equations would be essentially a multiple of the other, but this is not the case. If you wanted to verify this properly, you would, for instance, make vectors out of the 3 points. So take a vector from the first point to the second, a vector from the first point to the third, and check that the angle between them is not 0 or minus pi. Check otherwise that, for instance, one is not a multiple of the other, etc. But okay, in this course, we're not going to necessarily go into all the details, so a visual inspection, such as the one we've done here, will be sufficient, okay? So those 3 points are clearly not on the same line, so we can move on. So we know that such an overdetermined system is going to have no solution. So what can we do? Well, instead of trying to put a line through the 3 points, we're going to try to put a line that is the closest possible to the 3 points. Okay? So let me show you this. So here I'm, this is interesting. So I'll make a new slide. Let me get out of this. And for some reason, this is not a slide, but we can go back to here. So go back to this problem. Okay, so let me add to our original plot just the lines. Okay, how am I going to? I'm going to take the line that that corresponds to the solution to fitting the driving a line through the 2 first points we had. And to do that, what I'm going to say is, okay, so I'm going to create the matrix with the coefficients that we had, in this matrix. Where was it? Here. Okay, so I'm making this matrix M here, except that I'm calling it A, never mind. Okay, and then I'm making the matrix of right-hand sides, which is simply the vector 3, 5. Okay, so this is for the case of 2 points. I'm solving that one. And I'm going to find the solution by using this command. So it's solve, and what this says is solve the system AX, solve for X, the system AX equals right-hand side. Okay, and just a remark in passing, in R, if you want to invert a matrix, you actually just, and it's an invertible matrix, of course, you use solve without that second argument. Okay, so if I just go solve A, it will give me the inverse of A. If I go solve A right-hand side, it will give me X equals A inverse times right-hand side. Okay. Now, so this gives me coefficients. So again, I plot my points, but here what I'm going to add is a line. So this command add AB line just plots a straight line. There's several types of arguments that you can give it. One is the coefficients of the line. And I'm just going to point out, I have written my line as y equals ax plus b. R expects y equals a plus bx. So that means my coefficients are coming out in the wrong order. Okay, what I call A is what R calls B, and what I call B is what R calls A. But that's not really a problem, because all that means is that they're coming in the wrong order. And there's this very nice little command, rev, for reverse, that just inverts, changes the order, reverts the order of a vector. So if I go rev coefs, I get the opposite direction. Okay, so I'm plotting this line. I've got my third point that I've added. Clearly, this is not looking very good. Okay, so oops, sorry. Let me try another solution here. I'm going to make So I still have my matrix. I wouldn't have needed to do the computation again. Let me, while we're here, I don't need to do this computation again. Okay, I've done it already, so I can evaluate this. So what I'm doing here is I'm plotting again this first line, and then I thought, okay, I forgot the third point on the other hand. Oh, okay, this is interesting. Because I didn't evaluate this. Oops. Okay, I know what's happening. I did not evaluate this box. So in memory, it had x with 2 points instead of x with 3 points. So when I go here, it's going to have the 3 points. And when I go here, it's going to have the 3 points. So I looked at these 3 points and I decided that, well, using my nose, so guessing my way, it looked like a line with a slope of a half would be roughly good. And then I thought, okay, what's the intercept that would look quite well? Well, the intercept 3. So remember, as I said before, let me add this as a comment, AB line with arguments for y equals a plus bx. Okay, so this is what AB line thinks that a and that b that you're giving it as arguments here is doing. So here I'm saying an intercept of 3 and the slope of 0.5. And I'm making that that line red, and you can see it's quite good. And actually, so I'll mention, and I'll come back to that later, that I picked this sort of taking a look, and it turns out I found the solution just by looking at this without doing the computation. But you will see later in either in this video or the next video that we can actually compute this, and we can find that this a equals 3, intercept of 3, slope of 1/2 is actually the best solution. So I was quite lucky there. So this is quite nice. Okay, so we've got this line. It looks like it's passing roughly where it needs to, but let's see in more detail how we can do this. So I said we want a line that comes as close to as possible to the data points. So how do we know how far away we are? So we could use projections onto the line. So let me try to do this. I'm hoping you can see the mouse. I'm guessing you can. So if I am to project, for instance, onto the black line, so if these points are already on the black line, but I could project orthogonally, okay, at a right angle onto this, and I know that this projection is going to be the shortest distance between this point and this line. Okay, the orthogonal projection onto a line gives you the shortest distance. If I want to evaluate the distance between these points and the red line the same way, I would project orthogonally here and here and here and obtain a certain distance. The only problem is, okay, here I'm using the example of a straight line. I want to drive a straight line as close as possible to these points. But we will see soon that you don't have to put a straight line. You can take a line that is a curve that is more complicated. I mean, if you think about it, if I had a curve that was sinusoidal, for example, it probably would be much better. Okay, and if I want to project onto a curve that is a bit more complicated than a straight line, it becomes a bit more complicated to do that. It is feasible, okay, but it's a bit more complicated than we want to make things here. So instead of that, what we're going to do is we're going to look at, when we look at a value x, okay, something on the x-axis here, we are going to look at the distance between, so suppose I'm looking at this point and I'm looking at the red line and I'm looking at this first point. Well, if a point were on the red line, it would be here, okay? But it is here. So I can look at this distance between x equals 1 in the data point and x equals 1 on this line that I'm creating. The same way I can look at the distance between x equals 2 in the data point and x equals 2 here. So this is not the least distance. Okay, maybe I'm not getting the shortest distance, but it's still a distance that is going to vary, and that will be 0 if I am perfect. Suppose the 3 points are on the red line, then the distance between the red line and the points will be 0, even if I'm not looking at an orthogonal projection. Okay. So to illustrate this, first let's set it up. Okay. So I'm going to say that, and this is how we formulate the problem in general. So let me consider xi and yi, okay, the indices I, to be the data points. So here, for instance, I have x1, y1 equals 1, 3, x2, y2 equals 2, 5, and x3, y3 equals 3, 4. I could have many more. And when we come back to the example of the population in Canada, we will have 25 points, so I don't know exactly how many, but we will have a certain number of points. Now, again, I'm looking for an affine equation of the form y equals ax plus b, and to drive through these points. I mean, as close as possible, like we've done here with the red and actually also the black curve. Okay. Now, when I write this, I'm going to say, well, when I evaluate at the value x1 with the value that I've picked for the parameters, the unknowns a and b, then I get a y1 tilde, which is simply going to be a evaluate, the function evaluated at x1, y1, which in this case is a times x1 plus b. x1 being 1, this means that y1 tilde is equal to a plus b. The same way, if I evaluate at this point, then I get that y2 tilde, so y2 tilde is the point on that new line that I've chosen with coefficients a and b, that y2 tilde will be 2a plus b. y3 tilde will be 3a plus b. Okay. Now, if I look at the point at x equals x1, then the error I made by using the line y equals ax plus b, I can simply see it as the vector that joins my data point x1, y1 to the point on the curve y equals ax plus b evaluated at x1, that is x1, y1 tilde. Let me illustrate this. Yes, before I illustrate, I'll take the opportunity to introduce what we call functions. So those of you who are in a computer science type program, I don't really need to detail this, but for the others, functions are very, very useful constructs, and that really function, I shouldn't say function, that work the way as mathematicians or statisticians we think about the world, that is through the lens of functions. Computer scientists, they have another way of seeing the world. They love functions, but they also love objects. But for mathematicians and statisticians, functions are really the base. Okay, so a function is simply something that you can, well, it's creating a function. I don't think I need to explain more. So how do you do that in R? It's quite simple. You give a function name, so that would be like f for f of x, and you say what this function, so this is a keyword that you have to use, and what it depends on. So here I'm making a function of x, a0 and a1. Okay, so I should point out a function, let's say a function for y equals a, so let's, so here I'm using the usual notation, the one that sort of corresponds to what they are doing in R for AB line. Okay, so this is a polynomial of first degree with coefficients a0 and a1. So this is what the function is doing. Provided when I give it a value x here, a value a0 and a value a1, then what the function does, and this is a very, very simple function, it just returns a0 plus a1 times x. Okay. So this is really, really nice. So here I'm giving you an example. I'm evaluating this function at 3 points. So this first point is x equals 1, a0 equals 2, and a1 equals 3. I'll just point out that because I've given these arguments names, I can also put things in a different order, provided I indicate clearly what is what. So here, if you're not giving any names when you're calling the function, the arguments have to come in the same order as they're defined in the function definition. But here you see what I'm doing is I'm saying, well, that argument a0, I'm going to say it's equal to 2. a1 is equal to 3. X is equal to 1. In that case, I don't care about what order I'm doing things in. Okay. Another thing that is good is that functions are by default vectorized. What we call vectorized is that we can provide some arguments as vectors rather than as just points, and the function will evaluate at each point in the vector. So that first argument, that first call, is computing a0, so this is a0 2 plus 3 times 1, okay, which is giving me 5. That second argument is doing the same thing. That third one is doing the computation, but for x equals 1, x equals 2, and x equals 3. And you can see I get 3 results. The first one is like the other two, of course, because it's the same call. The second one is 8, and the third one is 11. Okay, so this is really, really useful, and you'll see in a second why. So let me show you what we get in the case of the points that we are considering. So here I'm going to say that A is 3 and B is 0.5. So remember, I'm looking at the in the same order as R imposes, or as we've just done in the function. So so let me just point it out. The curve, the line has the equation y equals a plus bx. Perhaps when I post those lecture notes online, well, these slides online, I will make sure that everything is in order a plus bx, but you see what I mean. So again, I'm plotting the points. I'm plotting the line. And here I'm making vertical lines. So this is yet another way of calling AB line. If you call it with V equals 1 or several values, it will make vertical lines at this 1 or several values. And let me make this a remark. If we used AB line of H equals 0, 0, 1, we would get, you can guess it, horizontal lines, sorry, my keyboard is weird, at y equals 0 and y equals 1, okay? And here, what I'm doing is I'm using that function I just defined, my line. I'm using it at those three x values. X equals 1, sorry, I can't select in a figure. X equals 1 here, x equals 2, and x equals 3. So what this does is it computes the value y equals a plus bx at, with a equals 3 and b equals 0.5 at the value x equals 1, 2, and 3. And I'm just storing it this in p. And now I'm plotting it. Okay, so I'm plotting at the x values 1, 2, 3, p, big red dots. And you can see, so these are my, in black, those are my data points. In red, this is the value that I get, the yi tilde that I get by using this value of a and b that I've selected and computing y at these points. And so the error that I'm making is the distance between that red point for each x, the distance between that red point and that black point. Okay, the red point is what I have because I've fitted this line through, and the black point is my data point. And what I want to do is to minimize the distance between these points. Okay. Now, let's go back to that error that we wrote before. So I said the error is simply the vector between the red and the black. Okay. Now, if you look at this vector here, what you have is, well, you simply compute. So what's the values of the vector that goes from x1, y1 to x1, y1 tilde? Well, it's simply x coordinate, subtract the second part. So subtract this one here. Oops, sorry. Subtract this one here from this one here, and subtract this one here from this one here. So I have x1 minus yx1 and y1 minus y1 tilde, which means that my vector has coordinates 0 and y1 minus y1 tilde, which you see here. Okay, so each one of these vectors that I have, they're vertical. And now what we're going to do is we're going to call epsilon 1. So here I'm looking at the point 1. Okay, I'm going to call epsilon 1 this distance here. Okay, so what you get is epsilon 1 is the error made when using the values a and b by, well, I mean, the error that you make by using these values compared to what the real data point is. And we can, the same way, compute epsilon 2 and epsilon 3, okay? What we do is we take those and we put them in a vector. For each data point, I'm going to have an error epsilon I that corresponds to the error that I get from using a and b in my equations. In my equation, yeah. And then this is a vector. I can compute its norm. And remember that the norm of a vector is its length. So when I compute the norm of E, I have a measure, let's say, of how much error I am making in my approximation for the A and B that I'm using. And you can guess what our problem is going to be. I want to find the V, A, and B that are such that E takes the minimum value. Okay, so as I just said, the norm of E is giving me the error that I make for the choice of A, B that I'm using. And so what I want to do is I want to find the pair AB such that the norm of E is minimal. So you can use several different types of norms. So we didn't go into details, and this is something you probably haven't seen very much, but in your future life, let's say, you will probably encounter a variety of norms. You know the Euclidean norm because that's the one we use all the time in early algebra or various mathematical topics, but there are other norms. For example, we could have a norm that takes the sum of the absolute values of the epsilon i's. There's also a well-known norm also, that is the maximum of the values of the epsilon I. But it turns out that the Euclidean norm has some very, very nice and interesting properties here and more generally. Okay? So very, very often you'll use the Euclidean norm. And here that's what we're going to do. So the Euclidean norm of E, we saw that in the review, but just as a reminder, it's the square root of the sum of the squares of the values. So here the Euclidean norm of E is simply the square root of epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared, which in passing means that when I'm computing the vector here, it doesn't matter whether I say x1 y1 tilde 2x1 y1 or vice versa, because I'm going to end up taking the square of this difference. And of course, it doesn't matter whether it's y1 squared minus y2 squared or minus y1 tilde squared, or y1 minus y1 tilde squared, or y1 tilde minus y1 squared. Okay. So to state the problem in a formal way, because that's really helpful, suppose I have a collection of, let me edit this, I have a collection of data points, x1, y1, to xn, yn. Then what I want to do is find the coefficients a, b of the line, and as I said, let me start making this consistent with what we're doing. Oh, okay, no, so for the moment I'll stick to this one, but never mind. As I said, I'll post a revised version. But I want to find coefficients of this line such that this norm, which is this sum of differences, is minimal. And here, this is in the case where yi tilde is axi plus b. Okay, so yi tilde is the value that I find when I evaluate at the xi in the data points. Okay, so that's our problem. And what I'm going to do in the remainder of these slides is to show you how to do this using what we typically would call brute force. And it would even be more than brute force. It would be a hack in a sense, because this is not an exact solution. I'm first going to show you how you can approach this problem from using a computer. So we have the 3 points. They're in the list points. Okay. We've made this function myLine, which computes the y tilde given an x and an a and a b. So what we are going to do is we're going to make a new function that takes just as arguments, it can take more things, but if you provide it with a value of a and b, it will compute e, the error. Okay. Let me make this like this. Okay, so we'll also pass the points, and I can pass the points, just because it's easier to have most things handy. So what does this function look like? And let me explain a little bit what happens. So this function, I'm going to call it error. And error takes as arguments the values A1, A0, and A1, and the points. And then what it's going to do is first it computes at the points, at the x values of the points, okay? So points dot $x, it computes the values given that A0 is equal to the A0 that comes here as argument, and A1 is equal to the A1 that's passed here as an argument. Once it has these points, these values, and these are, actually, maybe let me make this more explicit. Let's call it y tilde, okay? So I compute my y tilde, and my error is then the original value minus the values at the y tilde. So these are my, I should say, actually, perhaps epsilon, to make things really match what we are doing in practice. So epsilon is the vector. Actually, no, it's still called E. Sorry, E is the vector. So what it's going to do here is going to take every single point y, so that's the y values, and subtract to it the y tilde. And then my result is this. So what do I do? First of all, I square the entries in E. So E is going to be a vector. In the case that we're considering, it's going to have 3 entries. Okay. I take the square of the entries. And in R, when you want to take an entry-wise, I mean, an entry-by-entry square, you just take the vector and use this notation, square. Once I have this, what I have is epsilon 1 squared, epsilon 2 squared, epsilon 3 squared. So now I need to sum epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared. And sum is simply the sum of the elements in the vector. And then I take the square root of this sum. Okay. When I evaluate this, and you see changing the name of the internal variables has changed nothing. Let me evaluate this. What's the error that I make when I take 2 and 3? And what's the error for A0? I don't change the points. And what's the error that I make when I take A0 equals 3 and A1 equals 0.5? Well, that's the error for these two values here. And this one is the error that we get here. Now, we could do this by hand a little bit and say, well, perhaps, for instance, let me say, oh, maybe my error would be a bit better if I made my my intercept, let's say 3.1 instead of 3, and I made my my slope a little less. Well, you can see that actually it's not bad, but it is bigger than the one we have. And as I already pointed out, it turns out that almost randomly, I picked the optimal solution here, but never mind. Okay. The important thing is we can't be doing this by hand. You imagine yourself doing this repeatedly, typing away on your keyboard at different values and checking which one is smaller. And what I'm going to show you very quickly, I said I would hack a sort of computer-based solution to this. I'm going to use a cool little algorithm, um, which we call a genetic algorithm. So let me explain how this works. So genetic algorithms, so these are what we call stochastic, as in random, okay, optimization methods. There's other types of optimization methods that you can look at. There's many other types. Actually, optimization is a topic on which there's a lot of research going on because it's a very important problem. It occurs in a variety of domains, and so it's something on which there's entire labs working. I'll point out we have what is for the moment a third year course that is in the data science program on optimization. I think the plan is to make it a fourth year and graduate course. This should happen probably by the time you get there. I think it should take a year or two. It's an important course, and students in stats and students in computer science, even not in the data science program, are taking this course. There's a colleague in physics, for instance, who's done a lot of work on optimization. I mean, it's really, as I point out, a super important topic. A genetic algorithm is one optimization method, and it's called genetic algorithm because it mimics genetics. So the idea is to mimic the evolutionary side of genetics. The idea in the concept in genetics is that if you take a population, the natural tendency of a population is to move towards what is called a higher fitness. Okay, so better individuals that are better equipped for dealing with a certain type of problems tend to survive better, and therefore in later generations, they that trait that they had that made them more competitive tends to become more and more present. Okay, so what genetic algorithms do is they consider that the value of a function is actually its fitness. So if you want to optimize a function, if you want to maximize it, then you can work a bit like genetics. So the idea is that you try genes, and our genes here will be the variables, the unknowns that we are looking for. So our whole problem is to find values of A and B that are such that some criterion is maximized. Okay, so for the moment we're thinking about maximization because it's fitness. And I take these values of A and B, I'm going to take a bunch of them. I'm going to take a lot of genes, which each one of them is going to be two values, A and B. And I'm going to evaluate the fitness of all these genes. So that means I'm going to evaluate the function value for all these different random values of A and B. Well, the good ones are the ones that maximize the fitness. Those good ones I'm going to keep. And what I'm going to do is then I'm going to say, well, if they are good, they can be close to something really good. So maybe a little mutation can take place. And a mutation will be essentially, I have a value, let's say 1, 1. Well, I'm going to mutate and go to a value 1 and 1.01. Okay. I'm also going to implement what are called crossovers. I mean, I'm not going to go into the details. If you're interested, there's a lot of things about genetic algorithms. So there's a variety of ways to evolve this pool of genes, which are the function unknowns, I mean the A and B's that we're looking for. We're also going to throw random new ones in the population. So we keep the good genes and we throw in some random new genes and etc. And what we do is we look at how things evolve through generations. And after a certain number of generations, these algorithms usually converge to solutions that are maximizing the fitness. Okay, it's actually mathematically proven to be a good way of optimizing. So let's do this. So I'll make the remark just in passing. This that I've commented out, if you're running the code on CZG, you'll first need to uncomment this because GA, for genetic algorithm, is a library and it's not installed by default on CZG. So what you're going to need to do is install the package. And to install an R package, you just go install packages and the name of the package between quotes. When you do that, let me go back to this guy here. What's happening is in your, yes, I need to authenticate. You see what I was saying about getting the program, leaving this Jupyter Hub page up, because here, if I go, let me just make the remark. Here, you see it says forbidden. I wouldn't have been able to save, but now that I re-authenticated, I can click on forbidden and it doesn't reappear, which means I can now save. Okay. So let's go back here. When you've installed, when you did the install packages, the first time it will have created a subfolder here in your main Jupyter Hub page, which is called R. And oh, that's an older one. Okay, I'll need to update this. And it creates a folder that depends on what version of R you're using. The latest is 4.0, or actually it's 4.1, but we seem to be using 4.0 here. And here it's installed the packages that I'm using in a variety of contexts. Okay, so if you use this install packages, it will install the package the first time. Afterwards, you don't have to worry about it. But that means also, just in passing, that when you go to your home folder on Jupyter Hub, you'll have this. Don't delete it, otherwise you'll end up reinstalling the package every time. Okay, so back to the slides. So, as I said, first time you run this code, uncomment this first line. You load the package by just issuing this command, library GA. So library just says load a library. GA is the name of the library we want to use. And you see that here, by the way, you don't need the quotes. And then using GA is very, very simple. So, but there's one thing that is a little complicated here. So let me explain how this works. So the first one, so you just call GA, the function. Once you've loaded this library, you will have access to this function. The first type of argument is what type of genetic algorithm we are looking at. So I'm not going to go into the detail, just use real valued. And you see, you need to define a fitness. So I said the fitness is, sorry, let me walk back just a second. I said first that a genetic algorithm maximizes. By default, and most genetic algorithms, all they know how to do is maximize it. in our case, we want to minimize the error. So what do we do? Well, it's very simple. You see what I've done here. I've said that my fitness was minus the error, because maximizing minus the error is equivalent to minimizing the error. Ideally, so when you put minus the error, the result is going to be negative. And what is going to happen is my best solution, or my desired solution, is going to be a solution that has maximized this negative error. That means something that is going to be very close to zero. Okay, so if you want to minimize a function with a genetic algorithm, you simply say that you want to maximize minus that function. Now there's a little trick here, because the function that we made, error, it has several arguments. So this is something that is worth seeing done once. So it's got 3 arguments. It has A0, A1, which are the things we want to optimize. But I've also added this third argument, points. This is not something I'm going to optimize with respect to. Points is just something that I'm providing the function error so that it can do its job. But it's an argument. So we have to trick, what happens is we have to trick the function, and we do it this way. We say that the fitness is a function of x, and x here is what is going to vary. And so we say that A0 is going to be the first component of x, and A1 is the second component of x. Okay, so x is going to be a vector, and it's going to be the elements, the entries in x that are varying, that are the genes, okay, the components of the genes. And I don't care about points. So I'm not saying x of points or something like this. I'm just indicating that these 2 things are the things that change, and that one doesn't. If I had a simple function, if, for instance, my error function did not have had a single argument, sorry, if it was a function of just x, but a scalar x, then I wouldn't have to do this. But for any function of more than 1 variable, you have to do something like this. Just, okay, remember that this is how it works. Suggestions is simply, okay, let me give it some hints as to where it should start. Okay, so here I'm saying, well, perhaps my intercept is 2 and perhaps my slope is 3. I don't know. Lower and upper give you lower and upper bound for the values that you're providing. So what lower equals 0, 0 means is that I'm not allowing values of A0 and A1 to go lower than 0, 0. And upper equals 10, 10 means that I'm not allowing values more than 10 for those 2 unknowns. Okay? And this is very convenient, okay? And it makes a lot of sense, because when I'm creating my population of genes, I'm just going to take random values. All this means, lower and upper, means that those random values that I'm going to take are going to be between 0 and whatever value I indicate. Population size, this argument here, is how many genes is in a generation. So population equals 100, population size equals 100, means that at every generation, I'm going to put 100 genes. And when I initiate the process, the first generation, actually one of those genes is going to be the one that I suggest here. Okay, the one that has A0 equals 2 and A1 equals 3. Others will just be taken at random between lower and upper. And finally, max iteration, 150 here, is how many times how many generations do I consider? So I start with the first generation of 100 genes. I get a few good solutions in there. I put them aside. I mutate. I throw in new values, etc. This gives me a second generation. And I repeat this 150 times. So now let me show you how quickly that runs. I'm going to evaluate this here. And that's it. Plot GA just plots. So this shows you the fitness value. Okay, so minus this is the error. It shows you the fitness value. So the green curve is the best fitness value obtained. The blue is the mean here that you see. And the sort of shaded region is where the median is. Okay. And you can see that in 150 generations, my best value has reached a value that is relatively good. I'm very close to zero here. Okay. I'm still having some variety, of course, because it's a genetic stochastic algorithm. Until it's done 150 iterations, it's still throwing in random values and trying to see if it can find a better value. Okay. So you saw how fast that was, by the way. Okay, that's almost instantaneous. And here it's done 100 times 150 evaluations of the function error. Okay. So that's something that works quite well. Let's see what the solution looks like. So if I look at GA, if I just, sorry, I should point this out here. I've said this GA is simply I've put the solution in this variable. Okay. So GA is an object of class GA. So when I issue this command, it's just showing me what's happening. Okay. So it's an object of class GA. And this is a summary of what happened when you call the function. So the call was with these arguments and available slots. When you see the word slots, this means this is a different type of object in R than the ones we've met so far. And when you see the slots, this means that to access entries, instead of using $ like you would do when you have a list or a data frame, you have to use this ampersand here. Okay, so you have to use at. So these are the slots, and so that means these are the components that I can access. And so if I go GA solution, it will show me what values of A0 and A1 in my vector, so X1 and X2, it has found that give me the lowest fitness value. And I just run this, so the solution that you're seeing here is not the one we just created. Let's see what this gives. It's actually not super good. Well, I mean, knowing that the solution is 3 and 0.5, but it's not too bad. You can see I'm at 2.99 and 0.50. And the fitness is the value that we find. Okay, so the value of the function at this point, x1, x2. Just by curiosity, let's run it again and see if we get something that is better. And by better, I mean closer to, why is there an extra line here? No, oops, what did I do? I don't know. 2.99. Let's make it run a bit longer, or let's make it a bigger population. Perhaps if we increase the number of genes, we'll find better solutions. And of course, it takes longer. What I did. You see, so here I've gone much, much closer to what I know to be the true solution. So I'm at 3.0000099 and 0.499999. So clearly what I have is quite a good solution. And this is the error that we get with a, actually, let me maybe put it like this with a minus sign. This is the error that we get when we use this value of A0 and this value of A1. Okay, so we found something that is quite nice. Oops, I did not evaluate this. The next video, I'm going to show you that actually we could have done this computation by hand in a much easier way. Okay, and so you will see that mathematically it is possible to solve this problem in a rather elegant way rather than using brute force as we've just done. But I also wanted to illustrate the fact that, you know, there's good algorithms around and it's good to use them. And we'll come back to our original problem, which was the census data, after the next lecture, the next video that's going to detail the math aspects. And that's it for this video. I need to